Thank you for joining us. I'm Ed Hoffman, the Director of NASA's Academy for Program, Project, and Engineering Leadership, and I'd like to welcome you to Masters with Masters. These events pull together master practitioners who share their lessons, thoughts, and insights pertaining to managing major programs and projects. Today we have two leaders and distinguished pioneers who've worked many issues related to Mars-type programs. I'd like to first introduce you to Dr. Rudy Schmidt, who's the head of the Telecommunications Satellite Programs Department of the European Space Agency, a position he's held since July of 2009. He was also project manager for several of ESA's Directorate of Science and Robotics Exploration programs, and also led the Mars Express, Venus Express, and Gaia project teams. Welcome to Masters with Masters. Also, I'd like to introduce Rob Manning. Rob is the Mars Exploration Program Chief Engineer at the Jet Propulsion Laboratory. He's also the Chief Engineer for the Mars Science Laboratory mission and has been the Chief Engineer for other Mars missions, including the 1997 Mars Pathfinder and the Mars Exploration rovers, which landed the Spirit and Opportunity rovers on the surface of Mars in early 2004. Thank you, Rob, and thank you both for being here.
Thank you.
You both get to work on incredible missions, and just the notion of Mars is something that excites people in general. I'd like to start maybe with you, Rob. What got you involved in the work in terms of aerospace and specifically around Mars?
Well, I've been excited about space since I was a little kid. I thought the idea of robots in space just seemed so fitting for my way of thinking, but I didn't really dream I'd do this until after graduating from college. I came from Caltech to JPL, and I found myself at the bottom rungs of JPL working out my way up as an engineer, and spending now 30 years here, learning all sorts of fascinating things about this business, and it's been an incredible ride for me.
What makes Mars so fascinating, do you think?
Well, first of all, the great thing for me, we had two very successful Mars landers in the 1970s, the two Viking landers, and they arrived on Mars. They looked around the landscape of Mars, did some sampling of the soils, and at the time was believed to tell us that Mars was a dead, sterile, lifeless, boring place. Well, in the ensuing years, there wasn't much work being done on Mars, but starting in the mid-90s, there was the Mars Observer mission, an orbiter to get back to Mars and try to look at Mars. Mars was still seemed like an enigma to us. You could see signs of water coursing over the surface of Mars, large catastrophic outflows of water. We see these fantastically interesting solar poles of Mars covered with both what we think was water, ice, and CO2. And we see what seemed to be a dynamic atmosphere with huge, fantastic dust storms. Mars was just a big mystery. It's still, at that time in particular, it was a very big mystery. So in early 90s, when I got a chance to have this fantastic opportunity to become chief engineer for Mars Pathfinder, for me it was a dream come true, because it allowed me to take all my childhood desires and put them together and took all the things that I'd learned in the 12 years leading up to that in engineering, and put them together with a small team to actually build a vehicle to go and land and actually move around on the surface of Mars, which was even more exciting.
Right. And Rudy, you led the Mars Express mission for ESA, which obviously is a collaboration of many ESA member states, complex mission, and then the science and the technology and the management. What is it that you have learned most in terms of your experience with Mars and with the collaborations and some of the experiences you've had?
Well, first of all, I would never have expected that I end up leading a mission to Mars, because I started in the agency, in the European Space Agency, in the early 80s as a scientist. Now I sat in my office doing data analysis, trying to conceive new ideas for new measurements of electric field, magnetic fields, particles in space. And then eventually I became project scientist for a mission called Cluster, and I spent my first 14 years in the agency I spent working on that mission. It was one of the old style, competition all the time to be the best out of a group of missions, doing design work, doing study work, redesigning because it's too expensive. And 14 years passed by, and then we lost it within 20 seconds after launch in 96. It was a big tragedy. And then we sat there in Kourou thinking, what do we do now after 14 years? And we conceived great ideas, and also NASA was involved in that mission as well, and together with NASA, we managed 1 year later to get the approval of Cluster 2. But at that point I thought, was enough of Cluster. And it happened without me realizing, because I was so focused on getting Cluster 2 going again, that Mars 96, the Russian Mars 96 mission failed, and some of the big European member states of the agency got together and saying, we have lost so much money, so much knowledge, so many instruments on Mars 96, we Europeans have to do now our own mission. And in 97, 98 time frame, that idea has grown to something that became discussable at top ESA management level. So at least there was a chance that money could be found. There was no money, but there was a feeling that money somehow could be found. And then I was asked whether I would take over, out of this cluster experience working with projects and things, whether I would take over the preparation of Mars Express. It was not the implementation, it was the preparation, because at that point in time, nobody knew whether we could launch it in 2003, whether the famous 150 million that were finally found in the budgets, in the coffin of the agency, so to speak, would be sufficient to build an orbiter, launch it, fly it, operate it. And that preparation period lasted until probably 99, maybe early 2000, that we could say, yes, we can launch in 2003, yes, we can do it with 150 millions, and yes, we have a good chance that we reach with the spacecraft the lifetime the scientists wanted to cover or to map the entire surface. And at that point I became Mars Express manager, but I already had built up so much momentum in this that I thought, now I've done the preparation, I'm not stopping anymore. Right. And of course we have a process, a very formal process to nominate project managers. I had to go through this, but I came then out in the end of project manager. So that was a quite interesting and hectic phase in my life.
It sounds like for both of you, the grounding, the initial interest was the science, maybe the engineering,
yes,
and then the management of the project came from that. To what extent is the management of such complex missions, is that a continuation of the science, or is it a different? Obviously, the work is different, but is there a sense that you're still doing it ultimately for the science and the technology, or did you see it as a separation point, the management from the?
For us, it was a bit difficult because it was the first deep space mission which we did alone. We had done, or the agency had done, missions like Ulysses or Huygens Cassini, but they were in collaboration. They were de facto led by the bigger partner, which was obviously NASA, and they were led by NASA, while Mars Express for the first time was a fully European spacecraft operated by us, implemented by us, but also with some NASA, with some particularly JPL instruments on board. But we did not really know whether we have enough experience, whether enough background and stiffness in the end to carry it through. So we took quite a careful approach in the beginning, trying to keep as much margin on our side, trying to list our top 10 risks all the time. I said to my people at that time, when I wake you up at 2 o'clock in the morning, without any hesitation, you have to give me your 10 biggest risks. Yeah. And that way we approached it. And we built up lots of margin, and then politicians told us you cannot fly to Mars without a lander. And then all the reserves we built up went into Beagle 2, which was the lander we had to carry to Mars in the end.
Right. That's a lot of pressure.
Yes.
Having the first Mars mission with a lander and the first mission that you had to do from scratch, owning it completely from top to bottom.
And this with little budget, with a small team. But the argument of my bosses at that time was, you don't take any risk because there is this big mission called Rosetta, which was supposed to be launched at about the same time, much bigger spacecraft, a much bigger project team. They would develop all the different technology, and you, Mars Express team, you just buy the recurring units, you build it in your spacecraft and you fly. But what happened in the end, our small team was much more efficient than the bigger Rosetta team. So a year into the development, we have overtaken Rosetta in terms of development. And the small Mars Express team started to drive the technology. So what we were not supposed to do, in the end, we had to do. And it was quite challenging or quite interesting as well. Because you do decisions without having, in several instances, you don't have enough background to make a decision. But you know the launch that is coming, so this decision has to be done.
That seems very familiar because my first Mars mission was Mars Pathfinder, which was a small fixed price, the first discovery mission along with Near mission. And so we had a very tiny budget, and it was considered to be extraordinarily small for a Mars lander, at least by compared to Viking, the missions, which were many times more expensive, at least by budget. But the best thing is having a small team. Now we had something that maybe you didn't have, and that we didn't have that kind of pressure. We were allowed to work in the shadow of a very large project that was going on here called the Cassini mission. Galileo had finally gotten off the ground and was on its way to kind of limping its way to Jupiter, but we allowed ourselves to have a very small project that worked. What they said was, in fact, we were told to work in the faster, better, cheaper mold. Now, those of us, because we're all many of us were very experienced, and so there were some people who were new to this business, but for the most part, we didn't know what that meant. All we knew is that we had to do a lander with very few, not very complicated requirements, to be honest with you. Land and do some science and bring a little rover with you. That was our Beagle 2. And so it made for a very exciting environment, because with a very small team of people, we could actually work very efficiently. And likewise, like with Rosetta and Mars Express, we had the Cassini technology that we could borrow from, and we in fact also beat them to the launch pad, and but mostly because we were small and much more agile. But unlike your project, we didn't have a lot of eyes looking at us. We were pretty invisible until the very end.
How does a program change when you're on it's Mars Pathfinder you're talking about, and any program, I think, to Mars would be very visible, but how is it different when you're managing or leading a team that's what you're calling a small project as opposed to large?
I think whether it's a high visibility project or not, if you can constrain the mission objectives, keep the system as simple as you dare, but no simpler,
right,
and make sure you don't bite off too much, and give yourself healthy reserves. I think one of the things we did was, even though it was a low-cost mission, we had initially 50% cost reserves, which is today unheard-ofly large number. In fact, people would laugh at you today if you said, "Here, I need 50% reserves." And so, well, obviously you don't know what you're doing if you're asking for 50% reserve. And that's correct. We don't. This is a first for us, and so we spent every penny of that 50%, by the way. But it worked, and it was very successful. Now, on the other hand, the risk model we were working with was not the same risk model that we would use today on, for example, the Mars Science Laboratory, where we had no redundancy to speak of, with very little redundancy. Just a few key places that we felt there were high-risk components, radios, pyrotechnic devices, a few other places that we put some redundancy in. But it was considered a relatively high-risk Class C mission, or the term that we used back then, the Class C mission, that allowed us to avoid having to prove that we were reliable under certain circumstances. So we were not a high-rel mission in that sense. But with the budget low and with a lot of encouragement, because we had so many missions that were very large, Mars Observer, very large, very expensive, very difficult mission to build, it had a lot of changes in its life, and so as a consequence, its price was very high. And there was a sense that we were building very large vehicles with lots of instruments on them, and it was all eggs in one basket. So maybe we should make the basket smaller and put one or two eggs in it rather than having so many. And so that was a motivator. But for me, it was still, I was motivated by the science was always up there. I've always, in fact, for me, we had scientists right outside of my office working and looking at Mars pictures from Viking and Mariner 9, and I realized just how little information they had had for all these years. It had been many years since Viking landed in 1977 until the mid-90s. So they were pining for information, and we could give it to them for the first time in many years.
Yeah. So coming back to obviously the purpose, the sense of the importance, and the the science. It's interesting you talk about, again, small versus large, because the nature of anything you're going to do is going to be complex. And I've heard some project managers say that they prefer doing large because when you're doing small, you can lose resources faster. Maybe you're not as. And I've heard the other thing, that there's the advantage of the small because you can kind of proceed without too much maybe help or interference. Any thoughts in terms of?
For me, it's very clear. After Mars Express, I'm a fan of small project teams because they're efficient. And Mars Express has shown we have overtaken a big team who followed the traditional approach of doing everything according to the book. A small team which is driven by launch date and constrained by cost has to be innovative. And I think one of my main tasks was to find out how much I can bend the rules and still being within the box a project manager has to be in.
Right.
And that helped us a lot. In the end, we launched one day later than we predicted 5 years earlier. But our starting point, compared to Rob's statement, our starting point was different because Mars Express is the child of a failure. We could not be a failure again. So we had all the eyes pointing at us. The Inspector General reviewed us over and over again to make sure that our margins, our reserves, our design assumptions, our requirements is all tight. And now every step, even with industry, we worked throughout to keep, at least we wanted to say we have done our best. Now, in the end, it worked out well. Had it not worked out, at least we could have said we have done whatever was possible in this world. We have tried to do to avoid that this is going to be a failure.
Do you manage differently? Both NASA and ESA have had remarkable successes. Certainly in Mars programs, has also had failures, very, very difficult outcomes. Do you change how you manage, or do you try not to change? Is there a, you try to be an effective, manager for a program no matter what the situation is, or do you notice, after a failure that there's a different way you have to approach things? Just because there is more visibility, there is more folks wondering.
Yeah. When the room for failure is small, because ESA is, what is it, a tenth of NASA or something like this. We have less missions. We had a Mars mission in 2003. We are going to have the next one hopefully in 2016. Yeah. While you have one every launch window, isn't it? That means almost every 2 years or so. Yeah. It gives you a totally different basis from which you start designing the next mission. And in addition, of course, we have other constraints imposed on us. This is that we have, by now we have 18 or 19 member states. The 19th is just coming in, so I don't know whether today at this moment we are still 18 or maybe already 19. But these member states, they have expectations, they have wishes, they have requirements, they have scientists who want to achieve something. So we have to bring not only the engineering side, but also the political domain under one common denominator and manage the project within these constraints.
Right.
I would also add, though, that the larger projects with the larger budgets also have more stuff to them. They're bigger for a reason, because there's more instruments. They either have a more complex mission definition. There's just more things you have to manage. And not just larger launch vehicles. It's just not a scale-up. There's actually more interfaces that you have to deal with. And as a consequence, you have to use more rigorous systems engineering techniques to manage those interfaces so that the various things that are going on in parallel succeed and they come back and they meet you at the end. For a smaller mission, you just have less things to manage. And that, as a consequence, you can apply different management disciplines to improve your efficiency, and without necessarily changing the risk posture. Now, in some cases, for example, MSL, where we were asked to put a lot of redundancy in, approaching the redundancy of some traditional large flagship missions we've had in the past. That means you have twice as much equipment to build. And you have more equipment to build, you have more stuff to integrate, more different permutations of testing you have to do. just a lot more complexity. And then you have to manage that complexity, you have to divide and conquer. And if you're going to divide and conquer, you have to wrap interface agreements, ICDs, requirements around all those pieces, and that just adds overhead and that you need to be successful, but it's an overhead that is an additional cost that you don't necessarily have to deal with in a smaller project. So scale matters.
But I'm not quite sure I fully agree with you, because my project following Mars Express was about 5 times the budget of Mars Express. Mm-hmm. But the project team size was far from 5 times bigger than the Mars Express project. It was probably 50% more people. I mean, instead of 12 people, it was 17 people of that order of magnitude. And still, the project, when I left it at CDR, moved on to other things. But until CDR, it followed quite nicely the projected schedule for the project. And as it stands now, it's still on schedule.
Did you use the same management techniques and
yes.
specification levels?
Yes. Actually, it was much more complicated in Mars Express because it's astronometry mission.
Yeah.
Very sophisticated optics. And, in the beginning, I thought it's all crazy what we are doing, but it turned out it was feasible. Measuring nanometers on a spacecraft, after the rocket shakes it, you still want to be within tens of nanometers accuracy of the optical equipment. So I thought it's never feasible, but European industry is able to do it, as we can show today. But so the much more technology risks. The spacecraft was bigger, therefore more equipment on board. Mm-hmm. There was an optical module, a big machine, and there was a service module underneath, also a big machine in itself. And I like small team, horizontal team. That means people close to the project manager, straight information path from as low as possible in the project team up to the project manager. Of course, you cannot have strictly a horizontal team. That doesn't work either. But minimum levels in it. That each person in the team feels responsible. He knows that he has immediate access to the project manager in case of a problem. No reporting, no team meetings, sub-team meetings, higher level, and then project team meetings, all in one go, all in one bag. And I think I like this. This is the efficiency you can achieve. I don't think you can go more efficient in a project team.
I think that's right.
Yeah.
And again, pertaining to the challenges, certainly NASA had a series of failures in terms of Mars, in terms of the faster, better, cheaper, feeling that perhaps the discipline maybe wasn't applied to it. From the standpoint of the lessons from failure, do you learn most from when things don't go right? That's a general belief. And what stands out most?
Well,
what changes you as a systems engineer, as a project manager, from things that didn't go right?
Well, there are things that failure does breed a couple of things. It allows the engineer to say, if there's a risk area, listen, I need to get resources to understand that risk. And in a project that is so cost constrained that they can't afford to even assess or understand the risk, then you're just skating on thin ice. And I think that was the situation we found ourselves with MPL and MCO, in that particularly MPL, where the team was so thin that there's so many technological and technology and even physics problems that they didn't have the resources to explore. Modeling they didn't do, analysis they didn't do, because they didn't have the depth and they didn't have the resources to continue doing those analysis and tests. So the one thing after failure is that you can say, listen, we've had these failures. I need the resources to do this work and to really understand, and particularly understand the things that are scary and the things that will bite you. And to do the tests and get the extra hardware, be able to do the parallel testing, get some development units. Don't just stop with the single set of test equipment or your unit or test that you're flying to Mars, but you build other test beds and other things that allow you to shake out the design and find all the holes in the design. And so, great thing about failure is that people start believing you when you say that, hey, there are issues that I need to solve, and I need to get the resources to solve them.
Right.
And now the bad thing is, of course, you also need a paper trail, and it's not necessarily bad, but now you need to have not just have done the work, but you need to have produced a package that you review with independent people who look over your shoulder, make sure that indeed you didn't forget anything. And so the second set of eyes rule applies. There is an overhead with that, but the flip side of it, especially something that's more complex, and certainly MER was much more complex than Pathfinder, the two rovers. So we were able to use those resources. As a consequence, MER was more expensive than Pathfinder, and we were paying a large part of that money. It was not just in hardware, but in actual additional work and additional double checking.
All right. So it sounds like what you learned from previous failures was make sure you have the proper resources to do what you need to do.
Exactly.
And take the time to go into a level of depth that you and the team is comfortable with.
Yes.
Is any thoughts in terms of from when things went wrong?
Yeah, as I said, my career almost, well, after 14 years, but my career halfway through ended tragically with this loss of the cluster mission, which de facto was a consequence of reusing software without thinking too much about the reuse. And of course, you will always, at least for myself, I will always remember, don't reuse without thinking, because you end up in the same situation. The software does something else than you expect it to do. But obviously also on Mars Express we had a failure. We had this Beagle 2 lander, which was built by a group of very, very motivated scientists. But one of their key decisions was, or design decisions was, if there was a margin, then put one instrument more on board, instead of provide hardware that gives you information on how the process during landing, entry, descent, and landing progresses. So we lost it, and we have no clue when we lost it, how we lost it, and what happened to it. So there was de facto, unfortunately, no lesson learned out of this. Right. Maybe the lesson learned is don't do it that way.
Yeah.
Right.
Yes.
Yeah.
Follow
Yes.
your system all the way through until it
That's something
ends
else
up
that,
somewhere.
I don't know if you'll remember this, but when you were going through the Mars Exploration Rover lessons learned, you had said from the previous failures, one of the things that stuck out to you was sometimes you just need to stop and reflect and think about what's going on. And it sounds basic, but it sounds also what you're saying. Sometimes probably the people in this field are always moving forward, moving out. Let's keep making progress. And the difficulty is to just stop and reflect and think.
You need that, and that's part of the resource story. Having a little bit of extra people,
Right.
a little bit of extra help, so that there are the key people who really understand the design can stop. It says, did we really look this through? What can ask the questions that don't get asked, that don't necessarily fall through the process, and say, well, did we really check that the system really worked? Now, I have to admit, there's a long list of reasons why MER failed but didn't. And that because we had such a compressed schedule, the big resource that was missing on that project was time. So reflection was at a premium on MER, and it was a premium on Mars Polar Lander as well, just because of the team size being so small. They did some fantastic things. Now on Phoenix, we actually bought ourselves some time and people to think through, particularly the entry, descent, landing problem. Now, it was the same landing architecture, same technologies, hardware and software systems that we flew Mars Polar Lander. So why would we think if MPL didn't land successfully, why would we think Mars Phoenix would land successfully? Well, we said, let's start it. Let's pretend like we knew nothing about it, and let's just take the design and analyze and test it as if it was a brand new design, and ignore the heritage argument because we had nothing to base it on. So we did, and in the process, we learned new things about Phoenix, and we learned new things about Mars Polar Lander as well. New things that we were able to integrate together and resolve with not a huge amount of money, but the time and effort it took to peel the onion and really understand what's going on, especially the physics, especially the hardware-to-hardware interactions and the system interfaces. And we learned a lot, and I think we know it made a fantastic difference, and Phoenix was a spectacular success as a consequence.
Right. And clearly part of the challenge you both deal with is you're not just doing the same thing over and over again. You're also being challenged to innovate, develop new technologies, take risks to have breakthroughs in technologies or in management or in cost. How do you measure that? How do you make that balance happen between adhering to risk, but also being able to innovate? What kind of decision process do you go through? What kind of a management approach do you go through?
I just to start, my biggest thing about risk, taking a risk, especially with technology risk, we rarely put a key technology in series of mission success if we don't need to. If we can get to our objective with something that's tried and true, or something, or a low risk, whether it's development or mission risk, we'll do it. But at the flip side of it, if there's a technology that we need to succeed, we will put our heart and soul into making it happen. And because it's on the critical path to mission success. And I think that's a very key point. A lot of people come and say, why don't you throw this technology? I say, well, because I can do this mission with this technology where I've already retired the risks, and so I don't need to do it again.
Right. So how do you balance risk and the demand for innovation?
Yeah, I think there's one thing. One is the plan you have at the beginning, and the other thing is reality when you are in the project. As I said, the plan was that we procure recurring units developed by Rosetta, and the plan was also that we refly the instruments of Mars 96. That means spare units from Mars 96. Reality was the scientists said we need new instruments because we learned so many things in building the first set of instruments. Now we do it differently. So we had suddenly a kind of new payload which was not expected to be there. So the scientists went off, new sensors, I don't know, new detectors, whatever. We found ourselves, as I said earlier, halfway through the project with the fact that the technology development by Rosetta was not fast enough with our progress needed for 2003 launch. So the small team then followed the scientists, making sure that at least we couldn't stop them developing new things because the payload is under member state control. We manage the interfaces, but payments for the instruments come from the member states. So we just gave them help as much as we could to be sure they come on time with the new instruments or modified instruments. And on the other hand, we also diverted our focus from following the industrial prime contractor by also following development of new transponders, new mass memory. Now, things we were assuming in the beginning just existing off the shelf for us. Right. So it was quite an interesting period.
That always happens.
Yeah. Yes.
It literally always happens. We inherited on MER. We based on that our architecture on the Athena instrument suite that was supposed to launch with Mars 01, which did not launch after Mars Polar Lander failed or disappeared. And we realized we had to change everything in order to get it to work because all the things we learned before. And quite frankly, that still was worth it because we got a high reliability design. We had a system that we knew would work because we didn't just buy a black box. It did cost us more, but I think had we stalled and found out too late that these problems were going to be in there, it would have been too late and would have risked our launch. And so, my view in the matter is put the time and money into your budget with this probability highly in mind because it's very hard to inherit bit for bit, wire for wire, box for box, and especially from one mission to another mission because the mission objectives change, the environment changes, the interfaces change, and our knowledge of the risk changes, right, most importantly.
And aero braking is obviously one of the breakthrough technologies, your area of expertise, and so you approach that the same way in terms of looking at over.
Yes, the great thing about, for example, I think entry, descent, and landing is that there is a heritage to build upon, and we do. We build, and it's a technological heritage, and it's not a hardware heritage. For example, the Viking missions developed something called SLA 561V. It's the same. It's very similar to the spray-on insulation on the shuttle external tanks. This material was validated and tested thoroughly in the years leading up to the Viking launch in the early 70s. We were able to adopt that technology directly, even for very different conditions. We had to make it thicker. We had to redevelop redefine the formula after a 20-year hiatus on Pathfinder. But we used that same technology, the parachute technology, the whole structure of how to get rid of your heat shield and how to get out of your vehicle, undress yourself. in just a few minutes of very dynamic, in a very dynamic environment. All that technology was built up from those 70s, and we've been building ever since until it fails us. And in fact, on MSL, that technology that we had relied upon for many, many years, for many, many missions, suddenly didn't work. We realized that Mars Science Laboratory, which has a 4.5 meter diameter heat shield, the largest circular heat shield we've ever built, anyone's ever built, and we found that on Mars, and you fly through the atmosphere, that the radiative heating environment is so great, and the shear dynamics is so great for a lifting vehicle, that that old SLA 561 technology just doesn't work. And so very late in the development, we had to put on the brakes and come up with a whole new technology and adapted technology that we used on Stardust, the Pika heat shield material. And that was a huge left turn, but it was done with our eyes wide open. Of course, going from, as a project manager, it's very scary going from a devil that you knew to a devil that you don't know. Mm. But this devil has worked out very well so far.
Yeah, we had an interesting experience in this context as well, because Mars Express, the project itself moved forward quite nicely, and we as project team, we have borne the idea that with all the leftovers, one could build a second Mars mission for a launch in 2005. And this idea in the beginning, people said, crazy, stupid idea. It does not balance the interest of the various research communities, because the agency has a kind of approach that each community gets a mission at a certain point in time. Maybe not every 5 years, maybe every 10 years or something like this, but they all served in the end. But doing 2 planetary missions after each other spoils it. But finally, the director, our director at that time, Roger Bonnet, decided, yes, we do that. And we, as I said, naively assume it's going to be a second Mars mission. That means, do the whole thing again, maybe different instruments, but the same spacecraft. But the director says, to be fair, we have to do competition, to open it to all communities. Using this bus, you can do these things with the bus, whether you do planetology, astronomy, whatever, provide ideas. So the ideas came back, and what did we get? We got a Venus mission. So our idea of, having a twin went out of the window. For the Venus Express mission, it turned out we needed a new solar array, because, temperatures are totally different at Venus than they are at Mars. We needed a completely new thermal system, because you have 2 solar constants at Venus, compared, was it half solar constant, whatever it was on Mars Express. So we bought ourselves a lot of problems, but in the end we also made this a successful mission, launched in 2005. Mm-hmm.
Yeah, so it's just working the balance,
yeah.
and staying attentive to that.
Were you able to stay within your cost reserve for
Mars Express? Yes, we did 2003. We did a backtracking of our numbers to 98. You call it dollars, we call it euros.
Sure.
And it turned out we were on the spot with the 150 million. Venus Express, I don't know, because I left Venus Express at CDR, I believe. So what the guys did afterwards, I don't know in terms of budget.
Want to switch over to international collaboration. Obviously, this Masters with Masters has two practitioners from ESA, from NASA, and most missions nowadays are international collaborations, whether it's science or human spaceflight. It makes sense to start, with Rudy. Everything ESA does is, in essence, a collaboration.
Yes.
19 European member states, Canada. How do you work effectively when you have so many different stakeholders and partners involved in something that's naturally complex?
It makes life more complicated, that's true. But on the other hand, from my first days in the agency, I've learned to live with it. So for me, it's nothing exceptional, nothing extraordinary. I know I have to satisfy the need of all the member states involved in a mission. And of course, what it means is, as project manager, you're not getting always the best company for a certain piece of hardware. You have to make compromises. You have to be absolutely sure at the end of the project that enough money went into various countries according to certain computations that we call this geo-return. That are constraints which probably you are not familiar because you don't have such constraints, while for us, for me, it's daily business. It's big fraction of my daily business, but it's something I have to do. It's the price for being a European.
Right.
And I think I like it because working with Portuguese on one hand, working soon with Hungarians, Czechs, Greeks, whoever else will join us in the future, is interesting because the cultures are different, the experience of the companies is totally different. In the new member states, you have to build up an industry because there's no space, factories, there's no experience even, but these companies want to learn. But of course, as a project life has it, there's competition and only one company can get a certain piece of software or hardware. That means they are losers. So this does not make our life easy because these losers will be unhappy because not only the losers themselves, but also their countries will be unhappy because not enough money is flowing back. At the end of the day, you have a balance sheet which shows lots of negatives for smaller countries because smaller countries typically have less companies where you can choose from, while the big countries have an easier life because you have 5 companies and you choose one of them.
Right.
And you have met the requirement, while in a small country you have one, and if that company lost in a competition, there's nothing anymore you can do about it.
And how do you manage risk across such a wider spectrum? Is it the same, or is it something you have to?
There is, of course, there is increased risk because we are dealing with companies who are not always standard customers for certain contracts. So these companies, to fill our geo return hole somewhere, we give a contract to a company, which is a new thing for them. And of course, this is a big risk because there are chances that this company will not be ready on time with the hardware. So we had recently a case, and of course I'm not going in details here, but what we have done, one of the project engineers was assigned to that company. He was a kind of resident. He trained them, he showed them, he explained them. In the end, the hardware came. It came a bit later, but it came perfectly working. And this company is very happy. Next time around, they will have a good chance to win a competition.
Yeah. So it's part of it's part of
Yes.
the business, and it builds up capability over time.
Yes.
And Rob, obviously, NASA's been heavily involved increasingly international missions. What are the benefits?
Well, certainly the benefits is from a just parochial perspective is sharing the cost of a project or for something that's very difficult. We've been looking at collaborating with Mars Science, Mars Sample Return for years. We have science instruments on board Mars Science Laboratory. We've been doing this for a long time. We had a fantastic relationship with the Europeans, CNES in particular, with the sample return missions plans in the late 1990s. So we aren't as good as it. We aren't as good as Europeans are at managing these complicated relationships. We are used to being able to solve the problems directly, finding the best, cheapest company, and going to them, and having the control on our side. It's a lot less work when you can just solve your technical problems, the lowest cost and the fastest schedule, without regard to having to satisfy these relationships. But the flip side of it is having a partner that actually can produce significant contributions that actually enable missions that you couldn't do alone. That is fantastic, and that's what we've seen over and over again. And so our biggest challenge now is how to be, especially given the ITAR regulations, how to do strong, technically challenging and exciting and with high return missions across international boundaries. It is difficult for us to do that, and we can learn. It can be done. Right. We just have to think it through very carefully and think through the interfaces carefully so that we can work in parallel and bring our vehicles together. Huygens Cassini mission is a perfect example of a pair of missions that work together to make an integrated whole. That just a fantastic relationship. It's the right kind of systems interface too that allowed these teams to work without having to deal with a lot of ancillary information, large amounts of technical analysis, and lower the risk considerably.
And I think, yes, I fully agree with what you're saying. And I think it's also relatively easy, I should say, for the European scientists to build up international teams because they have to bring in their own money. The agency is not paying for the instruments contrary to what you are doing. So the PI, when he submits a proposal, has to find a team that brings together enough money to fund the entire instrument he is going to propose. And I've seen PIs coming with a team proposal which de facto included scientists from all continents, which in one hand is easy because he just put names on a piece of paper. On the other hand, of course, he gets 25 deliveries. And he has to make sure that these hardware deliveries, they all fit together when he has to put them together and form the instrument he has offered in his proposal in the beginning. So I'm pretty impressed by the capabilities of the scientists, not only on our side but also on your side, to put together these extremely complicated instrument proposals with an even more complicated team structure behind it.
Right. Are international missions more stable once you've agreed to them? I know that I've heard people say that if you get to the point where you have the agreements go through, you're more likely that you'll go to the end of the mission.
Certainly, it's been true in the manned side of NASA. Yeah. It's been kind of a rocky road in the case of Mars sample return, in the sense that we're talking a lot of money on both sides of the ocean, and now you need the ANDED condition, of course, of both approving not just the total amount but also the phasing and getting the money to show up when you needed it in order to get the system to work together. And it's a challenge because it means you have to have very solid, well thought through interfaces and agreements that last. And it's difficult, and particularly that sample return. It's a difficult mission to chop into pieces, it turns out.
Right.
It's difficult to find those places where interfaces work well, but not impossible, just very challenging. So I would say the answer is we don't know. It's still an experiment again. And the initial conditions.
Clearly there's more strategic work going on between NASA and ESA. When I was in the cafeteria earlier, I saw some agreements on the news in terms of some of the Jupiter activities. So there's a sense that there's an advantage, which may be sharing cost, but also being able to do things that otherwise you couldn't do.
Yes. Indeed. Well, that's the whole idea. Do things that we can't do. One of the things that's happened is that for many of our missions, not all of them, but many of the missions are the ones that have gone on in the past have been the easier missions to execute. Now the things we want to do are harder and harder. Bringing samples back from another planet, going to asteroids, going and staying at Jupiter, landing in Europa, doing very hard things. And so as a consequence, the cost per mission is much higher. And in a relatively fixed cost environment, cost sharing is actually really popular. It really makes a lot of sense.
Yeah, no, I agree. I fully agree on that, yes.
There
are things which you cannot do alone anymore nowadays. At least we in Europe, we cannot do it anymore. We could not fly. I think we would not even have all the technology to fly alone ourselves to Jupiter.
Yeah.
So we have to work together.
And what are the skills? If someone's going to be managing an international mission, or they're going to be working the engineering systems or the science, what, from your experience, are the things that are most vital you need to be able to bring to working in international collaboration?
Yeah, for me it's probably difficult to say because I'm so used to it.
Yeah.
I'm used to work with Italians, with Swedish, with English, with Spanish. My team, even all my department, I have all nationalities.
Right.
And I learned, or you have to learn what are the strong points, what are the weaker points of certain people, and particularly how do they react in certain situations. Because if you have a stress situation, and people immediately panic, then you would think that these people are not really suited for a project environment where you almost have every day a panic. So I think in the end, quickly you develop certain criteria on which you base whether people fit in stressy situation or in other situations. But I think the willingness to collaborate is and the understanding of other nationalities and cultures is very important. And I think we have this in the agency, at least, we have this in our genes, in our thinking.
Your DNA.
Because otherwise you will not make career in the agency if you can't work with other nationalities.
Right.
Yeah.
Well, I think we have a lot longer way to go, actually, because our ability to get things done without these hurdles, without the challenges you have, has made us much more impatient organizationally. We want to get to our results sooner. We want to compress the phase A, B, C, D part of the missions, and so we can get to launch and get to your mission objectives as soon as possible. And oftentimes the money phasing is such that it's all glumped together in that the end game in particular. So what we need to learn is both at the practical project management level, but also at the programmatic level, that these kinds of projects take time. And take time to get these agreements together. It takes time to work out and get all the documents straight, to get the agreements really solid and well understood. So we have to learn some patience, as well as learning about the differences in culture, the differences in terminology, the difference in our ways of doing business, which are equally valid, but without a good understanding of the differences, we'll never succeed.
Right. So an understanding, willingness to collaborate, those kinds of issues become very important.
Yes.
I wanted to talk about unanticipated outcomes. You're involved in, again, work that is cutting edge. It's deliberately so. And so sometimes things come, there are outcomes that you didn't expect, which are probably positive, and other times it's negative. You were talking about some of the heritage hardware, the assumptions about using the Pathfinder airbag system for the Mars exploration rovers,
yes.
And how that impacted risk. What did you learn about that, and what's the notion in terms of heritage and how to approach that?
Well, it's interesting is that the process almost forces us to have split personalities, because on one hand we want to convince the sponsor of these projects to trust us enough to get us going and get us funded and get the work going. On the other hand, at the same time, so there's a huge emphasis on trying to utilize as much of history as you can. In fact, it's the right thing to do. Don't do work you don't need to do. Rely on the expenditures and analysis work that has been done in the past. Well, in the case of MER, for example, we said, well, we're going to use all that technology from Mars Pathfinder and simply adapt it, maybe with minimal changes or no changes, to the MER rovers and land them using the very same technologies. Well, it turned out that we generally did, but we didn't use the same hardware. In fact, all the hardware had to be redesigned. Virtually less than 1% of the total mass of what we launched was, in fact, heritage hardware from prior missions. We had to adapt everything, change everything a little bit to deal with the larger landed masses. And so, and we had to do this all in 3 years. The idea was that we already had Phase A. All we had to do is just clean up Phase B and go with CD right off the bat. Well, turns out we had to do Phase A twice and then Phase B twice, and it left Phase C and D to happen in 1 year. So it was a very, very tall order. But we did learn that as you said before, you can't necessarily trust heritage. You have to know what not only do you, even if you understand the heritage, you may not understand the application of your heritage. You may not know how things are different and how the mission itself can change the very foundations of those assumptions that you made at the beginning of the project. And so, to me, it's you just have to be quick on your feet, be willing to learn. When you find information that tells you that your assumptions were wrong, don't hold on to your old assumptions. Throw them all away. Learn the new ones and go forward. And don't be afraid to say, I was wrong. I was very wrong about that. This is the new right answer. This is the new reality. Let's go forward. And we did that a lot on MER, and even with MSL, which is a whole new design for virtually everything. The same thing has happened for us there too. It happens over and over again.
Yeah. Is it partly also the connection of human nature, of people wanting to be optimistic, particularly taunted people?
Yes, I think optimism. You need optimism. You need optimism. Otherwise, you wouldn't even start these crazy things. Right. But it's a very difficult balancing act, because if you're too pessimistic, you're not going to convince anyone, including your own team, that it's worth the effort.
Off.
Right. So you have to have that right balancing act of being deeply pessimistic and wearing rose-colored glasses that just balances the risk so that your credibility isn't ruined and either up or down with your sponsor or with your team. And so everyone has to believe in you to pull it off, and that means you have to be authentic. Right. And so that's the key to these missions.
Right. And Rudy, have you observed similar experiences of the optimism, maybe driving towards expectation of what we should be getting from heritage and unanticipated outcomes? And how do you deal with that?
I think if I link unexpected outcome to something, then it's automatically people for me. And it's the optimism of scientists, because scientists by definition have to be, well, I'm a scientist myself, so I know you have to be optimistic.
Right.
Otherwise you would not do science work. But unexpected outcomes, yeah. No, you have, or we had these regular meetings with the scientists, and as I said earlier, we have no contract. We're not paying the scientists. Yeah. So the scientists are free electrons in the system, so to speak. Right. And quite often they came with fantastically different ideas from what was agreed. So one day, relatively late in the project, driven probably by measurement results on their instruments, they came with the idea, let's change the orbit, for instance. Yeah. And this is the last thing you want, because all your computations, all your modeling, all the operational documents you've written for a certain orbit, for things happening in a certain sequence, and then the scientists come and say, change it, because we want to have it different. And there were other things of this caliber. In the beginning, I thought, now how can we ever go to the launch pad with such a changing environment? But in the end, I learned, of course, they want to get the optimum out of it. They have to deliver something to compete with their colleagues in the US, in Japan, in Russia, wherever. And they are our customers in the end. I cannot say, I ignore what you're saying is my spacecraft, and if you don't want, we don't fly your instrument. No, it's not the way. They are customers, and we have to satisfy these customers. So typically we went off studying the new requests. And I must admit, quite often we found what I originally thought was a pretty stupid idea turned out to be implementable one way or another. Maybe not always 100%, but to some extent we could implement and therefore please the scientists. But it doesn't make your life easy if you have if you keep changing. What you thought is a solid goalpost and you move it a meter to the left. Next meeting you move it a meter to the right. But that's the way, it is the result of working with people. No? People change their mind and you have to adapt to it.
And it's complex work.
Yes,
so
of course.
It's not going to be obviously going straightforward. It sounds like a key factor is being open to the perceptions and being open to listening to different folks, because the situation will change. I wanted to get to the last segment, which talks about some of your own personal inspirations. Both of you seem like you feel like you have work that you love. That's what seems to come through. And what I was wondering is, what is it that you love most about what you do?
It's not an easy question, because I'm not thinking about this regularly. Yeah. I just love my work.
Well, what do you like least about what you do?
Well, same answer. I don't know. I'm
you
not thinking about
okay.
it. No, but I think what I'm really grateful for is that the agency, the European Space Agency, gave me the opportunity to work on what I think were at least in my opinion, the most fascinating missions. Yeah. We had the first interplanetary mission under our own control. We went to Venus for the first time, spacecraft Venus Express. And what I liked when we had this launch, after the launch of Venus Express, I thought the agency is controlling the 3 planets, because we had Mars orbiter, we had a Venus orbiter, and of course we have the Earth observation program in the agency. So we monitor 3 planets which have gone in totally different directions in terms of atmosphere evolution, environment evolution. One is cold, the other one is hot, and our dear Earth is heating up, but it's still okay here. So it was quite interesting, and I also always appreciated I had the privilege or the pleasure of working with what I think were one of the finest managers in the agency. Was my former director, former project managers like John Gredland, who is probably very well known here, and Dave Dale. So I think I was really lucky in my career to...
With your mentors.
Yes,
and with the
yes.
Work.
I learned a lot from them, yes.
Yeah.
Yes.
Rob?
Well, I feel just as lucky. I being in the right place at the right time didn't hurt, but the best part was being there in the revolution, in fact, of rediscovering Mars, and the whole unfolding from one mission to another, including Mars Express, including Mars Reconnaissance Orbiter, the Odyssey mission, on and on. Every mission has turned over a whole new page of our understanding of this planet, and we've gone from a fairly almost cartoony view of what Mars was in the early 70s, and even with the Viking missions, to an encyclopedia of understanding of Mars. Of course, each new page asking bringing up all those more new questions about Mars. But being part of that revolution and being an enabler for those discoveries has been very exciting for me, and I'm very, very proud of the fact that I was able to play a role.
Any mentors that stick out as Rudy?
Oh, certainly. Brian Muirhead, Tony Spear, John Cassani, people like that here at JPL. Is Tabak, from chief engineer for the Viking mission. Jim Martin, the project manager, fantastic disciplined thinker that influenced me greatly. Gentry Lee. I have these fantastic long list of great people.
Both of you have a lot of people.
But their experiences layer on top of each other and provided a foundation for all of us who've been part of this fantastic renaissance and exploration.
And final question for each of you. What is it you would advise to others who are starting out in the field? Very briefly.
Be curious.
Curious.
Work hard and learn as much as you can. Be as broad as you can. Be as open-minded as you can, and listen well. And if you can do all those things, and then learn to take that information and communicate it back to others and to yourself, you'll be a very good engineer and a good leader too.
Ready?
I think the key word for me, or the slogan for me, would be efficiency, because I can see how it's getting more and more difficult to get money for the business we want to do. And of course our missions get more expensive because we are wanting to go to farther planets, we want to go look deeper into space, we want to do more and more things for which you need detailed analysis, very, very sophisticated instruments, and even big instruments to collect, for instance, in astronomy enough light. So I think these missions in future we can only do if we have an extremely lean approach to the implementation. That means the project team must be efficient, industry must be efficient, and also the scientists must come up with clever ideas which on one hand give world-class science, on the other hand are reasonably cheap, that they remain affordable.
So frugal innovation will be key. I want to thank Rudy Schmidt of the European Space Agency, Rob Manning of NASA JPL. Also want to thank our partners from ESA for helping to sponsor this, as well as our partners from the Jet Propulsion Laboratory, and specifically Brinley McGowan for helping to set this up, and the JPL studio for furnishing this wonderful environment. So thank you until next time, and I enjoyed it a great deal.
Thank you.